You're live.
Okay. Hey everyone, I'm Lily. I'm currently the avionics lead on MIT rocket team, and today I'll be talking a little bit about the avionics on our rocket. So first I'm going to go over the team overview, just so you guys kind of get a picture of like what we do and what our mission is. So the mission of Rocket Team is to develop the engineering, teamwork, and leadership skills of the next generation of rocket scientists. And our current goal is to design, build, and launch a rocket beyond the Kármán line and into space. And just for reference, the Kármán line is the internationally recognized boundary at 100 kilometers above the Earth's surface, where space begins. So a little bit about the team history. So from 2016 to 2017, the team's main focus was on designing, building, and launching competition rockets. So on the left, you can see Therion, Virgo, and Raziel, which all placed at the Spaceport America Cup. And then in 2018, the team's focus shifted towards reaching space with our Hermes-class rockets. And Hermes 1, 2, and 3, which we've launched over the past few years, were high-speed, high-altitude demonstrators, providing the foundations for our team to reach space. And on the right, you can also see that we launched Staging Demo 1 and 2, which were created to test our staging capabilities for future rockets. And so the success of Staging Demo 2 paved the way for our current two-stage rocket project, Phoenix. Okay, so if everyone could turn off their cameras just for a hot sec, I'm going to show a quick video of one of our rocket launches. All right, let's see. I'm going to go no audio, by the way, for this. So. Okay, yeah. So that was what you just saw was the launch of Staging Demo 2, which is the first successful two-stage rocket that we launched. And essentially what this means, and you probably saw this in the video, but it's a rocket that has like two stages. So it's basically two rockets stacked on top of each other. So the booster, which is the bottom rocket, it basically gets both of them up to a certain altitude, does the burnout. Then the second one has less mass to carry up, but it has its own motor, so it can fly even higher. So that's kind of the architecture that we're going to be following for Project Phoenix, which I'll go into next. Okay. Oh, sorry. Okay, cool. So now on to Project Phoenix. So this is what the team is currently working on. So it's a two-stage rocket designed to reach 65,000 feet. So staging demo 2, which you just saw, reached around 33,000 feet. And some of the features for Project Phoenix include a passive staging mechanism, which we also was the technology that we basically proved to have worked during the launches of Staging Demo 1 and 2. We're also featuring a dual deployment recovery system, carbon fiber composite fin cans, and custom flight computers. And today we'll be focusing a little bit more on the electronic side of things. So, yeah. Okay, so now I'm going to go over what avionics as a subteam does. So avionics as a whole is just in charge of the integration and creation of all the electronic systems that fly on our rockets. So what does a complete avionics system look like? I'll go into this a little bit more later, but essentially an avionics system consists of flight computers, multiple flight computers for redundancy, which I can talk a little bit more about later as well as any supporting hardware that's needed for these flight computers to run. So some of the things we work on, so mainly are the flight computers, but also like making sure we can integrate all the batteries, switches, any data collection devices we need, and antennae, cameras, etc. And all these go inside the rocket, and we work with all the other sub teams to ensure that like we can integrate this all in like a timely fashion and in a way that will work with the rest of the rocket. So this is like in general, rocket team is a very like cross-disciplinary team, and we all kind of like work together while solving problems. So yeah, so I've thrown around flight computer a little bit. And so another term that's often used for flight computer is also altimeter. But first I'll just like go over kind of like what goes into a flight computer and like what exactly a flight computer is. So the main purpose of a flight computer during flight is to log data, send that data back to the ground station. So us on the ground, we call that providing telemetry, and to fire the pyros after doing estimation and modeling. So I'll go into each of these things a little bit more later, but first, just really quickly, the hardware anatomy of a flight computer includes having a CPU, so kind of like the processor in your computer, except much smaller. We call these microcontrollers. So if you've ever used like an Arduino or something like that, it's kind of like basically a processor of that size. But like the one we're using right now is also a little more advanced. In order to do data collection, we also need sensors. So this can include like barometers, accelerometers, gyroscopes, etc. Actuators. So our recovery system is powered using like pyrotechnic devices. So there's like a little black powder charge that ignites and basically allows the rocket to separate. And then we also have a radio. So like I said earlier, one of the important things that a flight computer does is transmit telemetry back to the ground station. And so in order to do this, we need some way of communicating like over the air without like Wi-Fi or anything. Again, along with a flight computer, we have like miscellaneous peripherals, so LEDs, buzzers, etc. So once the rocket's on the pad, we can't like see any electronics or like really like poke around with it. Like once it's already inside the rocket, it's like it's this big tube. There's a motor inside that's very explosive. So to get around this, what we do is like we send out beeps using buzzers, and also use LEDs that we can see through like the rocket body tube. And here on the right is a picture of a half-assembled Pixida, which was the flight computer that we worked on for the past couple of years. It doesn't have all the components on here, but here's the CPU, and then there are various sensors scattered around. So yeah. Okay, yeah, so a little bit more about how a flight computer works in general. So there's information from the world that's like happening all around as the rocket's in flight. And basically this information is sensed by like our sensors. So this includes our GPS, our barometer, our IMU, inertial motion unit, which basically is like an integrated accelerometer, gyroscope, and magnetometer. So these sensors get all this data from the world, then it feeds it into our microcontroller, aka our CPU. So it calculates all this stuff with sensor data, which I'll get into a little more later, but we call this kind of like estimation and modeling. So it sounds like an easy problem sometimes. It's like, where is the rocket right now? And it's like, you just use the GPS, but there's like a little more to that. GPS has like lower update rates, and like we need more precise readings. So basically our microcontroller, like we program it completely to just take in all the sensor data, calculate everything. Along the way, it transmits radio packets back to us. So while it's in flight, we can track it. And then when it figures out that we're at apogee, meaning the peak of the rocket's flight, it fires the pyros, which in turn deploys the recovery system. So now I'll talk a little bit more about Avionics' primary focus, which is Project D.E.N.NLS. So D.E.N.NLS stands for Data-Enabled Numerical Navigation and Ignition System. And essentially, it's the first iteration of our space-capable avionics system. And so some of the goals of D.E.N.NLS are to accurately and reliably fire the pyros with an advanced estimation and modeling system, collect data and maintain telemetry link during flight, and support a more modular design to fly in rockets of any size, stage, and capability. So a couple of challenges. So We basically wrapped up the Pixta project, which was a very good like learning project to learn how to actually make a flight computer and how to design our own circuit boards and how to program an entire embedded system from scratch. But we realized that we needed to basically start a new system with like the space requirements from the get-go, which I'll talk a little bit more about later. But so some of these things, so maintaining a telemetry link during flight, we had a radio link with Pixta as well, but we need to realize that like, hey, we're going for 100 kilometers at this point. Like that's you need a greater radio and like a greater power budget in order to reach that, which is kind of like essentially, so when you're designing an embedded system from the ground up, you need to figure out like what your requirements are. And so we basically just reevaluated like, hey, like space is going to require a whole different set of requirements than what we designed before. So some of these things include like going over 3 times the speed of sound, experiencing all these vibrations on the flight up, experiencing all these like new environmental pressures and stuff. So like once we're past like certain altitudes, the environment just gets like more and more harsh, in terms of like you get lower pressures, you get lower temperatures, etc. And also like I just said, at greater altitudes, it's much harder to communicate. So you have to like keep all these things in mind, and like a lot of these requirements come from talking to your other sub teams, so like structures, propulsion, etc. But also a lot of it comes from like learning from your past mistakes, which I'll talk a little bit more about later. Okay, yeah, so here's kind of a hardware overview of our boards that are going to fly on Project Dennis. So Dennis, like Project Dennis is kind of like the avionics system we imagine as a whole, and like Dennis is like what we called our main flight computer. So here Dennis is, yeah, the main flight computer. So this is the thing that has all the sensors and the CPU and does the computation. So basically it runs a real-time operating system, and it collects all the sensor data, does all the computation, and commands the different things around it. So we also have this RF amplification board on the side. So this is a radio amplifier. So again, at 100 kilometers, that's like you need a much greater radio budget in order to maintain a stable link for that. So that's why we decided to go with the RF board here instead of doing it on the main flight computer, which we actually did before. So some other supporting hardware includes a camera breakout, power distribution board. So earlier I said that like a lot of the things that informed the design for Dennis has come from like past flights and past failures. So one thing we noticed in like our past 2 rocket launches with Project Pixita was that doing the integration of all the avionics together tended to take a very long time, like many hours, and it took someone pretty specialized to be able to do it properly. And so in order to cut down on this, like we realized this is pretty infeasible as especially as our rockets get more and more complicated. So this is why we decided to just go with a power distribution board. And in this case, like what it basically does is it takes a bunch of batteries, which we've chosen to be compact yet like hold enough power for what we need, and just produce different voltage rails. And this also supports our goal of like having a modular design. So another one of the things that we were thinking about is that like this flight computer should be able to fly on rockets of any size, basically. So we've chosen, or our next project is for it to fly on a 2-stage rocket. And on a 2-stage rocket, there are many more events that happen. Like there's the first stage ignition, there's the first stage burnout, then you have to do the second stage ignition and the recovery for the second stage, which requires a lot of things. And basically for the power distribution board, like we can kind of pick and choose what we want to fly. So say we wanted to fly a different class of rocket. So if it's someone's like, if it's another Hermes class rocket, like we can basically, the way we modify our avionics system, we can support it very easily in terms of power budgeting. Okay, some other supporting hardware, so cameras. So another pain point that we learned from the last launch was that you don't want any cameras with buttons ever. There's kind of a funny story about that. So we had like these cameras with buttons, and someone like reverse engineered them by probing different points of the circuit board inside, which is like a really hacky solution, which in general you don't want to do for like, especially for rockets and aerospace. And basically what happened was that on launch, we had like 3 or 4 cameras and all of them were running except for one, so all of them were recording, but then the last one, as soon as the motor ignited, like, one of the buttons was pushed because of the vibration was so strong, that it only took a picture of the entire flight and not video, but we got video from the other one, so it's okay. But that's kind of like a funny little story. Um, and just like another thing to stress is that like generally in embedded systems design, like a lot of things that will inform your design decisions is like mistakes of others as well as like pain points of your previous flights and your previous launches, as well as like just talking to the other sub teams because it's like a whole team effort. It's not just like coding a thing. It's just like it requires a lot of like physical and human design like considerations. So yeah. And then lastly, another board that we have is the ground station. So this is a big part of what we do. We don't just launch it and like kind of search around. We launch it while like keeping this data link. And then we receive packets like every few seconds or like a couple every second. And basically then we can track it during flight. And also when it finally lands, then we can find it and recover it completely. Yeah. And so some other things that we're considering doing in the future include like a payload and an active stabilization breakout. And basically what a payload can be really anything. So sometimes people do like muon detectors or just trying to get more data from the rocket's like physical flight. And active stabilization, this is essentially like being able to correct the rocket like with using actuators in flight, because like typically we do passive stabilization just with the design of our fins. But yeah, and so another thing I want to talk about is redundancy. So here we have 3 other commercial off-the-shelf altimeters that are going to fly, and these are all powered off the power distribution board. And basically, you never want to put like all your eggs in one basket, basically, especially for like a rocket where you have like one launch and it experiences very violent forces during that launch. Because if you lose power or something goes wrong on one of them, you want to make sure that you have another one to back it up. So this is why we kind of have like this redundant design in place. Okay, yeah. So now here are just a couple of our selected components. And I'll just like quickly go over like kind of how we chose them and like features that we thought were cool that kind of contributed to the design. So first is our CPU. So the STM32H743 has a Cortex M7 core, is a very fast clock speed, and it has embed support. So on our past flight computer, the Pixida, basically we used the TNC as our CPU, which worked fine for what we needed at the time. But we realized that we want more like immediate responses and we want to be able to run like basically a concurrent operating system. So I'll talk about a little bit more about this when I get into the firmware features, but it had a very high clock speed, which is really great for an embedded system, especially like a rocket. And it like had just like a powerful enough computation power for what we needed. Next is our IMU, so an inertial motion unit. So our sensor data greatly basically is a huge factor in how good our estimation is. So basically like we want to have little noise while having like quick communication rates. And so this is kind of why we chose this particular chip. It also satisfied like our requirements physically about like what the max number of Gs our rocket was going to feel during flight. Lastly is the CC1200 radio. So it had a good data rate and pretty good specs in terms of output power and sensitivity, which we even boost using a power amplifier. And another thing is that like we used this chip before, so there's just like a lot of things that kind of go into the consideration for your design. So like sometimes you want to use chips you've used before just because you're more familiar with them. Sometimes you want to use a chip that's very commonly used. Like that's actually a big one. So like the STM series, like that's a very commonly used chip and like it has a lot of support. And like these things might sound like they should just be like on the back of your mind, but they're actually like pretty important when you're like deciding how to choose components and how to design your system. Okay, so now I'll talk a little bit more about firmware features. So For the first time, we're using a real-time operating system with Mbed OS. So if you've used Arduino before, you'll know that it kind of does like this iterative thing where it like loops every so often, and you basically have to run through all these steps every loop. But with a real-time operating system, we're basically just doing multi-threaded programming where we have different threads running and they keep switching off with each other depending on what task and priority. We're also going to be using an extended common filter for estimation, which is just an estimation algorithm where basically we take in all the sensor data and at every step it continues like correcting itself and giving us better estimates. Some other things that are in development are hardware in the loop as well as hardware out of the loop testing. So hardware in the loop testing is pretty important because it's hard to test something that needs to fly on a rocket, because it's like, especially for the particular rocket, you kind of have like one launch and that's basically it. And if it fails, it fails, and like you can do flight tests, but something that's really great to do to test your firmware is to basically spoof the sensor data and make it think that like it's basically running a flight, even though it's not like actually physically in a rocket and launching. So that's kind of what hardware in the loop is for. And then hardware out of the loop is essentially just an emulator for the STM32H7. And this is like pretty cool to use, especially given that COVID is a thing right now, because we typically kind of like pass boards off between each other when we're all at school. But having an emulator allows people to basically like run their firmware and make sure that there are no bugs like on their personal laptops before like trying to deploy it on a board or anything. So this has been pretty helpful during COVID. Yeah, so next I want to talk a little bit about system testing. So again, like one thing that's super important in general embedded systems, but especially in like rocketry, is being able to do the most extensive ground tests as possible, right? So like there's like all these little things that you don't know until you fly it, right? And so you learn these things over time, like as we've launched more and more, but there's still like all this stuff that we want to make sure we test on the ground. So I think I mentioned earlier, but like the environment at 100 kilometers is much different than the environment at like 30 kilometers, right? So something that we want to test is like, can it survive the temperature? Can it survive the pressure? Can it not only survive it, but is it giving us good data? And like, is everything operating as normal under these new conditions, right? So like going at like almost zero pressure, we need to make sure that our sensors can read properly at that environment, as well as like we can estimate properly still. And similarly with temperature. So another thing when choosing components is making sure that like all your chips can like survive like these lower temperature ratings. Okay. So some other things are forces. So again, there's like all these things about rocket forces and stuff that it feels during flight. Like there's going to be a lot of vibration. You're traveling at over 3 times the speed of sound, etc. So you can't like simulate all these things on the ground. Like simulating going 3 times the speed of sound on the ground is, I don't even know how to do that. So we do the best we can though by doing like impact testing, basically like throwing the whole thing on the ground, seeing if it breaks, seeing if it's still operating as normal. That's something that's really important. It might sound scary, but if things do break, I'm glad, like you're gonna be glad that you caught it then before you launch and like be able to fix it rather than finding out when you're launching. So that's something important that we do. Another thing is putting it on a vibe table and making sure that it can basically withstand these vibrations. And so this is kind of like another interesting thing that is like not super well defined as well, because some sensors and some electronics, they can do weird things when it's vibrating at certain frequencies. And also like things as simple as like connectors and solder joints and stuff, like bad things can happen. So this is another thing that we want to test, like doing as much like physical testing as we can. And then finally, like some things we are also planning on doing are like L2 and L3 test flights. So essentially what people on our team do are like get their certification rockets. And so this is really good for testing those like you're like crap, I'm right about to launch and there's this thing I need to do, right, that you won't necessarily like have found out beforehand, right? Because there's always going to be those like, oh crap, it's 3 a.m. I'm supposed to leave for the launch in like 5 hours and I still haven't figured this thing out, or this thing is going wrong and I need to be able to fix it. So it's really important to, like basically test it like you're going to launch it. In this case, you're actually launching it, but just on like a smaller rocket, which doesn't necessarily, perfectly simulate it, but you're never going to be able to perfectly simulate it. You just want to basically do everything that you can, right, in order to catch as many problems as you can before you're actually flying it. Okay. Okay, cool. Yeah. And so just to recap, like we are flying the system on Phoenix as well as like any other rocket that we're planning to fly in the future, but Phoenix will kind of be its like first like MIT rocket team test flight. Um, So some of the avionics, just to quickly go over the systems, are on the booster. We're basically flying a bunch of commercial off-the-shelf altimeters, as well as cameras plus supporting hardware. So um, we have commercial altimeters that we've used before, as well as antenna, so we can communicate with ground station, plus batteries and a beeper to aid in recovery. And then on the sustainer, our avionics get a little more sophisticated. So here's where we're actually piloting like the D.E.N.NLS system. So we have like the D.E.N.NLS custom flight computer. We have the power distribution board, which I talked a little bit more about earlier. The Pixta, our old flight computer, as a data logger. So even if like a flight goes wrong, like we want to make sure that we have good data on it. So it's important to like make sure we still have like these devices to log as much as we can. So when we want to launch next, we can figure out, and when we're designing like other future rockets, like we know, hey, this is kind of what happens like with two-stage, and like here's what's happened last time, and here's like just like all this data that is very useful for us to use. And then again, for redundancy, we have like the Telemega altimeter and the Raven, which are both commercial off the shelf, which we've used before. And then we have 18650 batteries, so this is just part of our power architecture. And then we have antennae and beepers. So yeah. So that's just like a quick overview of what we do on avionics. So I'm here to, if you have any questions about our system or in designing embedded systems in general. Yeah, thanks everyone for coming. Okay, so I see one question.